Hello again everyone, hope you're doing well and thanks for joining us for another video. Now for centuries it's been an established fact that the reason ships sailing out to sea disappear from the bottom up is due to the curvature of Earth blocking our line of sight. Disappear from the bottom up is due to the curvature of Earth.
Right out the gate, he shows us the effects of an inferior mirage and calls it Earth curve instead. Not a good start, Dave.
Disappear from the bottom up is due to the curvature of Earth.
Demonstrate how that lens bends light waves to create a mirage. Ed brings in a helicopter.
Okay, come toward us at maybe 10 knots at 5 feet AGL if you can, over.
Just now, the ground is much warmer than the air above it. This creates a gradient of hot to cold air. And since cold air is denser or heavier than warm air, the two air masses create distinct layers. Those layers act like a lens, bending and distorting our familiar reality. The result is a classic mirage, where objects appear below their actual position.
As the helicopter lands, you see its landing gear begin to vanish into the mirage. This is only one of a few different ways bottom-first obstruction occurs on our flat Earth.
This sequence is one of my favorite sequences with mirages. You can see it in the distance. You don't know what that is. It looks like a spaceship coming at you. Yeah. It's a black blob, and this is on a highway in New Mexico. You have no idea what it is, and slowly it emerges. It still looks like a spaceship right there.
Yeah. It's floating in the air.
It's floating in the air. It seems to be floating in the air. But then when we get up here, you see it. It's a car with two trucks behind it.
Oh.
Yeah.
Yeah, that's amazing, isn't it? That just shows that your eyes can deceive you so much with this sort of stuff.
Well, it's not your eyes that are deceiving you. Your eyes aren't deceiving anything. What it is the lens of the air between your object and what you're seeing. That's the deception.
However, flat earthers obviously have to offer a different explanation, and the reason that I've seen most commonly given is due to the Rayleigh criterion, sometimes phrased along the lines of it's perspective or it's a limit to our vision, which it's not. So in this video I'm going to try and break down as simply as possible to show why. The problem with all of this is that objects disappearing due to being unresolvable don't disappear from the bottom up like flat earthers claim. For example, I had Brian's Logic arguing with me a while ago saying that
I'm not Brian's Logic, Flatzoid or any other person you have made videos about. Claiming to debunk one person's words does not debunk the entire body of knowledge that is out there. Oftentimes when angular resolution is up for debate, globe proponents along with some flat earth proponents will fail to mention the effects a visible surface has on your perspective. Any visible flaw, such as land and water, wall or ceiling will compress your visual angles when looking along it, depending on the distance from the surface. When there is no visible surface, such as looking up at the sky, your visual angles remain open. This all plays a huge role in how far we can actually see. We will go into further detail soon, but let's continue.
we can't see a 6-foot object 3 miles away, so therefore we can't see the bottom 6 foot of any object 3 miles away. But his reason for that was that it had to be either due to perspective or due to the globe horizon. That it can't be both. That objects can't appear to both get smaller and smaller as they get further away, but then also be blocked by the physical curvature of Earth.
Brian was partially right in saying that Earth curve calculators do not take any part of perspective into account, but of course angular resolution will always apply, no matter the shape of any surface you're on. Dave is simply taking advantage of a poorly constructed argument that failed to mention the proximity of a viewer to that of a surface.
Except you only have to stand next to an inclined road to know that that's not the case. You can see cars driving up a hill and they will appear to get smaller and smaller as they get further from you. Once they crest the hill, they begin to disappear bottom up. And that's because the Earth is blocking our line of sight to them.
The problem with the globe though, is that Earth hill or bulge is simply not there. This has been demonstrated in several different ways, including that of VHF waves and other line-of-sight technologies. Here are just two examples.
Before the start of World War II, German scientists developed a blind landing navigation system for aircraft. Essentially, aircraft tuned in to a certain frequency would know the location of the center of the runway by using a radio beacon as a guide. After World War II broke out, German military scientists soon realized that the same technology could enable German bombers to locate specific targets in England even in the darkest of nights. This secret system was called Knickebein. In short, the radio beam from a single transmitter would guide the German bombers on a line towards the target, but one beam could not tell the bomber when they were over the target. A second transmitter was set up so its beam crossed over the target, indicating when the airplanes should drop the bombs. British intelligence, led by R.V. Jones, slowly became aware that such bombing beams may have existed, and presented the information to Frederick Lindemann, Winston Churchill's leading science advisor. But Lindemann and others said such a targeting system would be impossible, because the supposed curvature of the Earth would block the high-frequency beams, because VHF waves do not even allegedly bend around the curvature of the Earth.
Dr. Jones took the message to Professor Lindemann, his old tutor and now scientific advisor to Winston Churchill, and tried to persuade him of the serious threat posed by the Knickebein beams. But Lindemann was not convinced, pointing out that at the high frequencies necessary for an accurate beam, the curvature of the Earth would prevent its being directed against targets in Britain.
Lindemann was conceptually and mathematically right. VHF beams would require a direct line of sight with the German bombers, and England was simply too far away. The first of these Knickebein transmitters was set up on Stolberg Hill near Denmark. Another transmitter was set up at Kleve in western Germany. Stolberg Hill was located 443 miles away from Derby, England. The hill was only 142 feet high, and the transmitter was 152 feet high for a combined height of 294 feet. Based on the globe math, the Earth's curvature would hide 118,425 feet. The other transmitter was in Kleve. It only has an elevation of 39 feet combined with a 100-foot tower. 139-foot height with a distance of 331 miles means that the curvature of the Earth would hide 66,722 feet. In other words, under the globe, a German bomber would need to be higher than 118,425 feet to be within the line of sight of the Knickebein system. But the maximum cruising altitude of a German bomber was only 19,200 feet. Without question, it was impossible under the globe for those German bombers to be within line of sight of the Knickebein towers. But Knickebein did work, and English lives were lost as Churchill's scientific advisors couldn't believe in the VHF Knickebein system when the Earth's curvature should have made it impossible. Very high frequency requires a direct line of sight. Wikipedia confirms the same as it reads, as the transmitters were more or less in line of sight to high-altitude bombers. This article here confirms it as well. But as I just showed, Wikipedia lied, as German bombers would have been nearly 100,000 feet below the globe's geometric horizon and certainly not within line of sight of the towers. There you have it. Only under the Flat Earth model could the Knickebein system work, and the globe propagandists have no counter-argument but to lie and claim that the bombers were somehow in line of sight of the Knickebein towers when that would have been mathematically impossible. German bombing beams proved there is no Earth curvature. Hello everyone. I first wanted to thank Scott from Israel for sharing this information with me. I hope you find this evidence as exciting and compelling as I do. In short, this is another world record proof of the flat Earth. This evidence alone ends the globe. The world record comes from this website called The Things Network. I'll have a link in the description. As the title states, this was a LoRa radio transmission at a whopping distance of 830 miles or 1,336 kilometers. For those who do not know, LoRa is actually becoming a very important method of communication, and it also has tremendous potential for long-distance flat Earth testing. Here's a quick video clip describing what LoRa is.
LoRa stands for long range, and it's a relatively new communication standard targeting low power, long range, low bitrate communication. So it's really finding applications in Internet of Things, remote sensors, anything that requires low power consumption and a moderate to low bandwidth.
LoRa is in the ultra-high frequency UHF radio bandwidth, between 860 to 930 megahertz. It is important to note that UHF does not, even allegedly, bend with the curvature of the Earth. In fact, according to this website, LoRa is line of sight. According to the article, LoRa's range depends on radio line of sight. Radio waves in the 400 to 900 megahertz range may pass through some obstructions, depending on their composition, but will be absorbed or reflected otherwise. This means that the signal can potentially reach as far as the horizon, as long as there are no physical barriers to block it. In other words, LoRa communications end at the alleged globe geometric horizon. But this world record LoRa communication was at a distance of 830 miles. What makes this even more remarkable is that the LoRaWAN trackers were placed on a fishing boat and a buoy. Here are the pictures. This world record communication occurred at almost sea level. Assuming an observer height of 20 feet, that gives us a globe target hidden height of 448,550 feet, or 85 miles. At only 20 feet, the signal from the boat should have been blocked by the supposed Earth's bulge at around 5.5 miles. There is only one reasonable conclusion. The Earth has no curvature. The Earth is flat.
And it can't be that we can't resolve the bottom 6 foot of objects 3 miles away because of limits to our vision, because that would then mean that we couldn't resolve the bottom 6 foot of any object that's 3 miles away. And yet we can resolve the bottom 6 foot of a plane when it's 3 miles away, no problem. We don't just see half a plane suddenly cut off.
That's because there is no ground to compress your bottom visual angle while looking at objects in the sky. It's not until they reach your visual horizon that things will be cut off from your view. It's time you learn this, Dave.
So this is across a lake nearby, which on a perfectly clear day, decent weather, and it's about 410 feet across to the other side, where there'll be a piece of debris that you will see here in a minute. So I'll go ahead and play. So I'm lowering my iPhone from about a 2-foot height down to just where the water ripples, and that's just when the casing on the iPhone just barely touches the water. Right there. So the camera is inverted. It ends up being about a ½ inch above the water. This is zoomed in. You can see the white piece of debris by the bench to the lower left of the bench across the way. So you'll see there it's gone, and I haven't even touched the water yet. There, I touched the water and it's back again. So I decided to put some measurements to this, which we'll discuss in a minute. I also want you to note that piece of white debris right there in the center of the frame that is very nearby, around 15 feet away. And how close that gets to the horizon as we lower our phone down. So these are some still shots from what I just showed. So again, distance is 410 feet, and that near field debris is the red arrow in the left picture there in the low aspect of the frame. And then as I at about a 2-foot observer height, and then at about a 0.5 inch observer height, you can see how high in the field that piece of debris got near the purple mirror inflection point or horizon line of this image. So again, keep in mind that if this is, let's say it's 10 to 15 feet away, and the distance between myself and the debris on the other side is 410 feet, that I am cramming 400 feet of information between the red tip of that arrow and the purple horizon line, which is a lot of information. And so what ends up happening is that your horizon shortens along the lower field, and whatever is there disappears into the essentially a gap that's formed. So again, this is just a typical photo with a iPhone camera about 6 feet off the water, and I am basically looking at a cresting wave, which you can see in the zoomed out photo. You don't even need to be zoomed in. You can see the little white dot that the arrow is pointing to in the middle of the frame, and then zoomed in you can see it a little bit better. But how far is that cresting wave, do you think? So when you analyze this, you find that it's essentially about a half mile away. Each halving of a frame puts twice the amount of information in the next halving. So you can look at the 50% numbers on the side. You can look at the amount of information that I'm cramming into each subsection. And again, the proof of this you can find when I analyze the hallway footage. And you find that in, again, the lower 1/4 of the image, I have 9 feet, and then it goes 18 feet, 36 feet, 72 feet, and it doubles each time. And by the time you get to the arrow point, it's only about a half mile, which means that if I'm a 6-foot observer and I see 3 miles, then I'm cramming 2.5 miles between the very top black line and the purple line horizon, which is quite a lot of information to be crammed in such a small space. So I'm not going to go through this in too much detail. I want this to be short. Just remember that as you lower your eye height, you're cramming more and more information into a smaller space, and it gets lost. So, but it remains 50% of your vision. So the floor is still 50%, even though you're not seeing as far along the floor. So what happens to that information in the distance? It disappears essentially into this what I'll term, I guess, a horizon gap. And again, more information on this you can find on my channel or with the discussion with Jeranism. Same thing here. Again, at different heights you can see how I'm compressing different information. So when I'm 8 foot tall, the ceiling is getting compressed, and as I get down to 1 foot tall or 0 feet, or essentially half a centimeter off, the floor is getting compressed. And this is just an aspect of how our vision works. It has nothing to do with curvature. So these spacings, again, just to reiterate, they are spacings along regular intervals that were measured, and you can see how that information changes as I alter my height to them. More and more information gets compressed into smaller spaces. And this is just taking them away from the photos to analyze them. And then putting kind of a side-on view, which again doesn't really exist, but just allows you to kind of conceptualize things a little bit easier. And some more math on how the floor tiles worked, the spacing along the lights, and how all the mathematics works out essentially to give us this halving phenomenon between each iteration of a frame. And this is at different heights, and again, how you see different aspects within each halving of an image, and how this phenomenon might allow for bottom first disappearance as the horizon along the lower field shortens, and we do not see as far along it. And what ends up happening is we form this gap of sorts in our vision. If we are close to the ceiling, let's say, and it were flat, we would have a gap along the ceiling, and we wouldn't see as far along the ceiling, but we would see as further along the floor. And the vice versa occurs when we are closer to the floor than we are to the ceiling. And my point with this is that we are always, when we are outdoors, closer to the floor than we are to the ceiling. So as I lower myself in this perspective here, and I have a light visible across about 400 feet or so, or 500 feet of distance along a hallway, you can see that the light is visible at first, and then as I lower myself, how perspective changes, and how at a certain point the light is no longer visible. And these are just everyday examples you can do on your own. So if we change our, if we go from a hallway into an outdoor setting and we just change our horizon distance, there's no reason why this isn't a different aspect of perspective. It's the same exact thing. We're just outdoors. And instead of looking at a flashlight, we are now looking at a cruise ship or a boat or something else going over what we believe is a physical horizon, but is nothing more than an apparent position of our vision and how our vision works along flat surfaces. So same thing again, I'm in here in a Walmart and then no light is visible. I'm along the floor, so there's no reason to believe why this aspect of vision would change if I were to remove the walls and the ceiling of this Walmart and extend this floor for miles and miles, and I were just to stand up. It would be the same exact phenomenon, but just occur further and further away. There's no reason to believe that this is curvature. So I just do that here. I remove the walls and the ceiling. I'm still on the floor, and then I extend my floor, let's say, to become some crops or something like that. It doesn't matter. And now I'm just looking at a tractor going off into the distance, and it disappears as well. So here's the footage with some more exact measurements, and this is just later in the day. And so you can see kind of what occurs along this flat surface. And I'm calling it flat because by globe standards, this is a flat surface. Essentially no bulge is apparent across 400 feet, but yet we have an issue here. So please watch.
Okay, here we are at the lake. It's a nice clear night, perfectly still waters. I'll put the coordinates on Google for where exactly I am across this lake, and the distance of the light height, the distance of the light height, and the iPhone height. Bye.
So here we are, we're taking it at 2.5 inches just to be in the middle of the light. Here's the setup. And there I'm just barely touching the ground, touching the water. You can see the ripples just starting as the iPhone case just touches the water. There's no immersion of the camera or anything under the water. And here it is zoomed in a still shot. Missing now. Slow motion. You can see the autofocusing occurring, and I stopped it here so you can see kind of that there appears to be basically a hard line on this frame.
There's a clear cutoff from the bottom up, and it's very abrupt.
And again, just some more slow motion of the other times that I went up and down. So these were the distances. So again, 0.1 to 0.2. I basically sat there for about 2 or 3 minutes and allowed the positioning system to identify where I was before I pinpointed each point, and that's very accurate for at least where I was. So could it be a few feet off one way or another? Sure, but roughly it's about 400 feet at least. Again, you can see the measurement of my iPhone case to the center of the camera, and it is about 1/2 inch. And you can see that I took the 2.5 inches for the height of the light, which was being generous. I didn't do the top of the light, which the whole light disappears, but I'm just going to do the middle of the light. And so some still shots again. As I'm about 1.5 feet off the water, you can still clearly see the light, and you can see a little bit of reflection on the water with the light, but the light is still visible. And then as I am 0.5 inches off, there is clearly no light visible whatsoever. And then in the bottom of I just took some still shots of how that, when it was autofocusing, and you could see the halo, and how that halo definitely appears to be cut off bottom first. So what should we be seeing if we were to be living on a globe? If this phenomenon right here is because this water is curved, and curved water is what obstructs our vision of things beyond a horizon, a physical horizon, then what should we be seeing? Well, the short answer is that we should be seeing this entire light. There should be no loss. And so the drop essentially should be about 0.004 feet, or about 0.048 inches, or which comes out to about 1.22 millimeters. And if you know how big a millimeter is, that's extremely small. And we are definitely far more than 1.22 millimeters with that light above the water. Furthermore, my horizon distance should be about 1,314 feet, which is well beyond the 400 feet that we were at. So by all accounts, we should be seeing this entire light the whole time. So if we go to some earth curve calculators, you can see again by their mock-ups that there should be nothing hidden in this situation. It should be completely visible with a globe with an R radius of 3959 miles. Or something else occurs in our vision to cause this effect. Once again, just confirmation that the bulge height is extremely small in this situation, and that the hidden height is nothing. So in this situation, this curve calculator says 0.3 millimeters is the bulge height, which is negligible. And again, yet we have 2.5 inches are being obstructed in this situation. So another curve calculator. And again, notice that all of them model this as if you are looking down across a bulge, and that's why things disappear, is because you are either leaning backwards and looking across a bulge in front of you, or your eyes are tilted down and the object is tilting away from you. That's how this is modeled. This is not how this works. So again, under no situation should we see this kind of obstruction. Some more earth curve calculators, again, 0 millimeters, 0 feet, 0.00 feet. One of them gave 0.237 inches, so one of them gave at least a 0.23 quarter of an inch, but that doesn't matter. Again, we were 2.5 inches off the water, and so there was no refraction. You could not really say that this wasn't a refraction phenomenon. If you were to go back and look here at these conditions, this is across 400 feet. It's crystal clear. The water is not moving whatsoever, and the temperature is roughly the same between the water and the outside air. It was a fairly warm night, so
Okay.
I'm not too concerned that refraction would play almost any role in this whatsoever. So being generous and negating the loss of our 0.5 inch observer height and granting 2.5 inches of drop basically as the midpoint of the flashlight, not the top even, what should the radius of Earth be if we're going to assume that bottom-up obstruction is always caused by curvature? So in other words, if I'm losing 2.5 inches across 400 feet, what kind of radius would that purport to, right? What kind of globe should I be standing on if bottom-up disappearance is caused by physical obstruction? So when you do the math for this using trigonometry, where our theta angle comes out to 0.0175 degrees, which is again close to 1 arc minute, and our height of about of 2.5 inches of drop, then you end up with 870 miles of R. So R is 870 miles in this case, which is well below the 3,959 miles that is purported to be. You can use an alternative method using the 8-inch drop approximation for the first mile versus our 2.5-inch drop over our 410 feet. You can just analyze the ratios between the two, and you get to something about 4 times greater curve rate because our obstruction is just too much. And so, or it's about 1/4 the R basically. So as approximation again, but you get something where 990 miles. So we can just kind of, you can average some of these methods together, and you can say that roughly we should be standing on a globe that's about a radius of 900 miles. We're just going to use it as an approximation. So our new Earth circumference is 5,654 miles versus the expected 24,800 miles that they say it is. So Earth is now 1/4 the size it should be, and it ends up being smaller than the Moon, using the rationale that this is a physical curvature phenomenon. So you can believe that, or you can believe something else is responsible for this bottom up first, or this bottom first disappearance phenomenon. So is information loss an everyday aspect of our visual horizons? Is it why is this occurring? Is it secondary to tangible surfaces? In other words, to our proximity to a tangible surface limits the amount of information that we're being allowed to process. So I just want you to focus on that. It may not be that the bottom of the objects disappear from being too small to see, but rather that the ground can only extend so far when we are close to it. We can only see so far along the ground. It's not so much the object itself or the bottom of the boat itself getting too small. It's the fact that you can't see that far along the ground, but it still occupies 50% of your vision.
So we have seen how mirages, and how your proximity to a surface or compressed angles will obscure objects, bottom first on a flat plane, even if it were perfectly flat. Another way objects can become obscured bottom first on a flat plane is simply due to foreground objects, such as uneven ground, grass, waves, swells, etc.
So now we're at secondary to small obstructions within perspective. So within our floor example here, the last 3 golf balls are all on the same horizon line, and they no longer ascend within perspective. The floor tiles are a bit uneven in this case, and if there were an obstruction nearby, say 7 feet away, it would obscure the image further away at 130 feet. If we are beyond the horizon line at 95 feet in this example, we have lost a height equal to d tan theta, or 130 feet times the tangent of 1 arc minute, or 0.55 inches. The golf balls have a diameter of 1.6 inches, so our golf ball is reduced to 1.6 inches minus 0.5 equal to 1.13 inches. Again, given an obstruction, or given the amount of set. So because perspective ascends quickly and then tapers, an obstruction nearby would completely obscure the bottom of an object far away. Using similar triangles, and assuming we are at the portion of vision where this perspective plateau occurs, again, typically beyond 20 feet or so, we see that if there were an obstruction 30 feet away, near that second golf ball, or just 6 millimeters above the eye line, it would be enough to obscure the entire golf ball 130 feet away. So we can have summarized this effect by stating small obstructions in the foreground obstruct distant objects. So if that doesn't make sense, maybe it will here if I explain the diagram. So the red line from the eye to the purple line is again going to have a rapid ascent rate an exponential ascent rate. And so we know that objects, even though they encroach upon that purple line, they don't actually start to set for quite a bit distance away. So that means that there's essentially a plateau or a table of an area or distance across which an obstruction along that point would completely obscure the object further down the road because its angular size is going to get smaller. And so we calculated that for the amount of the golf ball that would be missing at 130 feet, just from diffraction, we would get roughly 0.13 inches of loss. And so, or excuse me, 0.55 inches of loss, and that would give us about a golf ball roughly 1.13 inches tall. And so that's why I've cut off the bottom of the golf ball in the diagram. So that's what we're looking at. And so on the bottom right hand picture, I've kind of pointed to that golf ball that is 130 feet away. And so if we were to put an obstruction, let's say this blue triangle, and we were to put it in the nearby vision, let's say at 30 feet away, and I've kind of put that there on the lower right, I put the little blue triangle next to the 30-foot ball. But you can see how if I were to put that in line with the 130-foot golf ball, it would completely obscure that ball. And we can calculate that ratio or what height would be required to obscure that distant object by just using similar triangles. And so that's what I've done with that formula, solving for x. So in this case, x is 6 millimeters. So a 6 millimeter obstruction above the purple line completely obscures the entire golf ball 130 feet away. And so for the 1 centimeter, and this is for the 1 centimeter observer height, so an obstruction of just 3 millimeters would obscure the entire bottom half of that golf ball. We would lose the bottom half of the golf ball. So keep in mind too from our formula before that for the 1 foot observer height, knowing that 0.05% is taken up within the lower 1/4 of vision, only 1.56 inches is going to be within that lower 1/4 of the visual field. And when we lowered our height down to 1 centimeter, again, 0.6 inches takes up 1/4 of the image. And I also want you to note here again how when we had a 1 foot observer height, the red orthogonal lines where the corners met extended off into a distance roughly 2,600 feet away. But as we lowered our eye height, that vanishing point essentially became a vanishing line and merged into that purple line we see that is much nearer to us. So here's some practical examples. So given a 0.4 inch observer height with the 1 arc minute of resolution, what height of an obstruction 60 feet away would obscure 0.4 inches of light at the end of a hallway 360 feet away? So it's just the same thing. Now I'm using a flashlight and an obstruction instead of a golf ball and an obstruction. And so we find that just 1.7 millimeters would block the entire light 360 feet away. Same thing here. Now if I just stand up and I'm going to extend this to a further distance, given a 6 foot observer height with 1 arc minute of resolution, how big would a wave have to be 0.25 miles away to obstruct a 250 foot tall cruise ship 20 miles away? So it's the same relationship, 250 feet of cruise ship 20 miles away versus X amount of obstruction a 1/4 mile away, and you would get a wave of 3 feet. So a 3 foot wave just a 1/4 mile away that has encroached upon that purple line already because of the rapid ascent rate will obstruct the entire boat to 20 miles away. And a 1.5 foot wave, very reasonable, especially with choppy waters, would obstruct the lower half of that boat.
The peak of Mount Everest is 8,849 meters high and is 7,500 kilometers away from the UK. That means at that distance, the angular size of Mount Everest from the UK would be 0.06 degrees, so within the resolution limit of our eyes.
As you have learned, Dave, that would only be true if Mount Everest was floating high in the sky, without a surface to compress the angles and with no atmospheric conditions to obscure it as well. Those conditions will never exist, nor do they need to, for us to know that we can still see and communicate way beyond the globe's capabilities, as has been demonstrated numerous times.
And that's just the naked eye. Armed with the Nikon P1000, we should be able to see that thing clear as day. Now, I'm sure flat earthers will point out that we wouldn't be able to see that far because it wouldn't be clear as day. There would be clouds and bad weather between us and Everest. But the summit of Mount Everest is often above the clouds, and so are commercial aircraft at cruising altitude.
You seem as if you like to talk. I like to let people talk who like to talk. It makes it easier to find out how full of shit they are.
And yet I am still waiting to see a flat earther with the Nikon P1000 be able to show us Mount Everest from a plane over the UK.
That is a very specific request, Dave, and it would be instantly written off as something else, like a cloud, or as an error by the globe proponents and anti-flat earthers anyways. The fact of the matter is that we already have several observations from an airplane that debunks the globe.
You're gonna be totally amazed, folks. We'll be applying the principles of photogrammetry to the aerial infrared images that I've taken, and we'll be using professional software to extract the 3D models of our world, and the results are simply shocking. First, I'm gonna show you how it works. I took a trip from San Francisco to Portland, right past Mount Shasta, and here's a few clips. I also captured a set of images with my camera, as you can see here, as I was flying past it, because I knew I wanted to try out this photogrammetry. The software I'll be using is called Metashape, and this is how it's used. Photogrammetry software lets you input a set of images and then it processes them to create a sparse cloud of data points, and then you can process a dense cloud of points. Basically, it looks at the information in the images and how it's shifted horizontally and vertically to determine the depth. Also reads the information of the camera that's embedded in the images and determines the focal length in terms of pixels, etc. And thus it can determine the depth to the geometry. And the results are simply incredible, folks. I mean, just look at this stuff, you know, with a few images. I have a 3D model here of Mount Shasta that I can rotate. Now on the back side of it, there's holes because there's no information there. But if you want to create a full 360 model, you got to take pictures all the way around. The neat thing about the processing step is the software can determine where the photos were taken from. As you saw, it shows the images floating in the air and oriented correctly. So that's incredible. It's all built in the geometry and the difference of the imagery. So now let's apply this amazing technology to some extremely flat areas that I've imaged before in infrared, and specifically let's look at Michigan. Here's the flight path, the red line. I flew from Chicago to Buffalo this spring, and I was looking towards the north, and I took some really clear images, as you see right here. This area is usually covered in clouds, but this on this particular day, the western side was clear, as you can see here, and we can almost see Lake Michigan on the left, curving around way out there. So we're really seeing about, you know, over 200 miles out. But let's use this photogrammetry to determine the flatness. Is it really as flat as it appears? So here I've imported all the images, and I already ran the first step, which determines the location of the images and creates the sparse tie points. Looks like about 7,000 or so points, and we can rotate and look at it. So the software probably looks at the prominent features in the image and creates this sparse dense cloud, and then the following steps are more involved. But here we can see the cloud layer above it. You see that? There's ground points, and then there's a cloud layer. And look how flat it is. It's incredible. So now let's run the next step here. So we'll go with high. There's a few setting options there. We'll just leave it on the default. And we'll be generating the depth map. And it's gonna take a while. So I'm just gonna skip ahead here. Okay, so the processing is done, and now we have this dense cloud to work with. Wow, look at that. Whoa. You can even see the clouds. Now there's an artifact underneath it, right? The black thing. But by and large, all the data points seem to be accurate. And it even picks up the clouds. That is so cool. Yet look how flat that is. Wow, that's incredible. But look at that. Look how flat that is. Oh my goodness. That is incredible, folks. Yeah, look at that. See? It is pretty flat. Now, don't worry, we're gonna do a little bit more analysis here, but this is just a visual to get us all excited, because this is really incredible, technology, Before I was trying to determine land features. You look out there and you see something and you say, hey, there's some feature out there, and then use Google Earth to try to determine what I'm seeing. Now here, with this technique, the software probably does a correlation across the whole image or pairs of images and determines, points which are the same. So because we're in motion, right, things move differently in the image, and that's a powerful technique. You can now determine based on movement what is close and what is far. So here's one of the first, second, third, fourth, fifth, sixth, and seventh image. Actually, they're numbered the other way because I was flying from left to right. And so yeah, I had a good spread of images here, and it created quite a detailed map. Now there's one more step here that I haven't done. That's where it creates tetrahedra. I can barely say that word. So what we're looking at here is just a dense point cloud, and I don't know, there's a lot of points there, as you can see on the left. So let's go back to the tie points, because that had more information, and we could see the clouds in the distance, which are not here. So that's what I'm interested in. So here I'm looking at the tie points, the less dense data set, and we can see as I rotate it, I'm not sure if you can see it on your screen, there is points out there at a different height, right there. Those are the clouds in the distance, and the other points on the bottom, that's the ground, you know. Now if we go to the dense cloud, look at that. You see, it's only a portion of it, very close in, so it doesn't take all the points from far away, because the angles are too shallow, and you cannot, you know, do accurate processing. I probably have to study the different options and parameters that will let the software kind of extend the analysis. But let's go back to the tie points. Okay, and I'm going to rotate it. And look at those clouds there in the distance. Isn't that incredible? Wow. And now look at that, see? So there's more data out there that we need to look at. And now I'm turning it sideways. And you'll see a detailed analysis. Now let's move it to the right a little bit to fit everything in there. And those blue things are the image location, obviously. So now when I rotate it on edge, it becomes apparent that there is a difference between the clouds and the ground. Isn't that incredible? Oh my God, that's incredible. And see, the dense cloud is only close in, so it discards a lot of information out there. Wow, that is incredible. Look at that. Wow. This is amazing. So I'm going to do an analysis based on that, on this dense cloud. So let's create a line and match it to the ground points. Here we go. Here's the clouds on top, and down on the bottom we have the ground points. There we go. Right there. Let's move it a little bit. That looks about right. Let's zoom in a little bit. You see the ground points? Yeah, right there. Man, this is so flat. Oh my God. Look at that. This is incredible. So now, let's see, what am I doing here? So there's the clouds, right? Those are data points from the clouds in the distance. So it's quite a distance here. Okay. So now let's create another line to approximate the curvature. You know, we're probably seeing, I don't know, 200-300 miles. So I've calculated roughly how much you should curve. So I'll show you an analysis slowly, but right now I'm just kind of putting up a curve here, and I'm gonna bend it slightly. So see, there's an angle of about 2 degrees in 300 miles. You know, there's a curvature of about 2 to 3 degrees. So I'm just bending this right now. Oh yeah, that's what I was doing, yeah. So here we have a visual of kind of the curvature of the Earth, the supposed curvature, and then the data points extracted from photogrammetry. And it's quite a shocker. I mean, it is extremely flat, you know? Our eyesight was not deceiving us. That's incredible, folks. This is amazing, and we'll do another analysis shortly, but here, let me move the curve down a little bit. And so while I was looking at this, I realized, wait a second, I can determine how far I'm seeing based on the altitude of my photos, which are shown in the model. I know I was flying at 32,000 feet. Now here's the incredible result, folks. Shocking. By using the altitude of the images as a reference, I calculated that I'm seeing data points out over 500 miles, folks. This is just incredible. You see on the left, I'm flying at 32,000 feet. And I've determined the center of the images and the vector there. And now I have a reference height on the image, and then I've taken that and I measured horizontally, and look at that. My goodness, wow. We can go, there's data points even beyond 540, maybe 600 miles out. Now you can see the clouds, you can see the ground there, and I've also placed the curved Earth. I've calculated that to be accurate, and look at that. That is incredible, folks. Just amazing. I mean, what can we say? You know, the Earth is absolutely flat. It just boggles the mind. So,
or from a plane above the UK, it's about 3,500 miles across the Atlantic to reach New York, and a further 2,000 miles or so to reach San Francisco. That means from a plane above the UK at 35,000 feet, there is enough vertical angular resolution for the whole of America to be visible to the naked eye.
You're not going to make out 0.043 degrees through thousands of miles of air and water vapor, Dave. Any foreground objects such as waves that are just 0.05 degrees will also block your view. Our visibility from a commercial jet is going to max out around 1,000 miles in good conditions, and that is using an infrared zoom camera. Even at those distances and heights, the globe is debunked. Jtolan Media One has many more of these observations at his YouTube channel. You have to then force the claim that refraction somehow lifted up and stretched out miles upon miles from beyond the curve, flattened in such a way that it aligned seamlessly with the physical globe horizon, somehow giving the perfect illusion of a flat Earth. Complete nonsense that would never happen and cannot be accurately replicated or reproduced in real life. Recording that much land simply means you recorded that much land.
It's the deception.
You can see the halo and how that halo definitely appears to be cut off bottom first.
That's going to be it for now. If you've enjoyed this video and you haven't already done so, then please consider hitting the like and subscribe buttons, and then hopefully we'll see you in the next video.
Good luck. You're gonna need it.